Alright, welcome everybody. So today we're going to do a video on naming and formula writing for compounds. So hopefully by the time that you are watching this video, you have memorized all of the polyatomic ions and all of the monatomic ions. Memorizing both of those really is key to you being able to do this more easily. Now, can you look at your polyatomic ion sheet and figure out what the ions are? Yes. But in the end, you're going to need to be able to do this on your own without the help of those charts. Okay, so the first thing that we're going to do is we're going to talk about ionic compounds. Ionic compounds are the first type of compounds that we're going to look at. And when I name an ionic compound, first I'm going to do name to formula, and then you'll see on the next page I'm going to do formula to name. I think it's a little bit easier to do name to formula because it allows me to look at what's known as the Roman numeral or the name ending of the metal and figure out from there some cues as to how to name the compound. So, let's start with a typical name here. Let's start with something like, maybe sodium oxide. So sodium oxide is the formula that I want to write. I give you the name, you have to write the formula. Well, the steps are pretty straightforward. Write the symbol for each part of the name. You can use the periodic table and your memorized polyatomic ions. So the symbol for sodium is Na. The symbol for oxide is O. Now you might be wondering, how do I know that? How do I know that oxide is O? Well, I provided something for you in this slide presentation on page number 2, 3, 4, 5. I provided you something that I call your IDE guide. And your IDE guide is basically a guide to all the IDE endings. And so I know for each of these what the symbols are. If I'm fluoride, I'm F minus. Chloride, Cl minus, bromide, Br minus, iodide, I minus, telluride, Te2 minus, oxide, O2 minus, sulfide, S2 minus, selenide, Se2 minus, nitride, N3 minus, phosphide, P3 minus, arsenide, As3 minus, carbide, C4 minus, and silicide, Si4 minus. So these are my ides, and I'm using oxide in this example. So if we go back to page number 1 and we look at oxide, we know that it is just O. Now, what I showed you also was the charge. So we have sodium, we have oxygen, sodium oxide. Step 2 is to assign the charges to each part. So when I assign the charges, Na is in group 1, so it is +1. Oxide O is in group 16, and I also gave you the charge as -2. So now I have the charges for each one. The thing is that this is a compound, and a compound we need to balance the charges. The charges, the positives and the negatives, need to cancel out. And at this point, they're not balanced, they're not canceled out, so I need to figure out how many sodiums would I need and how many oxygens would I need in order to balance them. Well, what I do is something called least common multiple, down here at step 3. So the least common multiple between +1 and -2 is 2. So I would need 2 sodiums that are +1 for a total of +2. If I multiply them, I get +2. And I would need 1 oxygen at -2. And so my final formula for this would be Na2O. Now, what if I were to go about this and I were to try and do a situation where I had a polyatomic ion? If I were to do a polyatomic ion, well, let's try something like potassium carbonate. So if I were to do potassium carbonate, I would again go through the same steps. So first I would have potassium, K, and I have carbonate, CO3. And this is where knowing your polyatomic ions comes into play. If you don't know your polyatomic ions, well, then you're not going to be able to do the next step, which is the charges. And you wouldn't have been able to do the first step, which was to write the symbol. So now I assign the charges +1, -2. Again, they're not balanced. So now I need to balance them. I'm going to need 2 Ks. That will bring me, if I multiply them together, to +2. I need 1 carbonate, so I just don't put a number there. It's understood to be 1. And so my formula will be K2CO3. What if I were to have something that were to have a Roman numeral in it? Well, down here I say the Roman numeral is the charge of the metal. Let me show you what I mean by that if we were to have something that was to have a Roman numeral in it. So if I were to do something like copper 2, let's do phosphate. So copper 2 phosphate, how does that look? Well, copper is +2. That is what the Roman numeral tells me. Copper's symbol is Cu, and the Roman numeral, and I have it here underlined in bold and italic, that the Roman numeral is the charge of the metal. I put it in right away. And then phosphate, I know from my polyatomic ions, is PO4 -3. Well, now I have these 2 ions. I need to balance their charges. Their least common multiple is 6. So what times 2 would give me 6? 3 of them. What times -3 would give me -6 to balance it? 2 of them. Notice what I did with the phosphate. I put it in parentheses, and I do that so that I can isolate the 4 in the PO4 from the fact that there are 2 phosphates. So my formula, Cu3 PO4 in parentheses 2, is copper 2 phosphate. Now if you look in your monatomic ion sheet, copper +2 is also called cupric. And I could have given that to you. I could have given you cupric phosphate. In fact, we could do one where, like, I can do something like auric chloride. So now I need to know what auric is. This is where memorizing the monatomic ions is so important. Auric, if you look, auric is for gold +3. Chloride, Cl, if I go to my Ide guide, is -1. Now, if I need to balance them, I'm going to need 3 Cl's, AuCl3. Notice as a final thing about the naming, going to formula, when I write the formula, I don't include the charges in the end. I leave the charges out. I just have the subscripts. Okay, what if we were to go the other way? What if we were to do ionic name to formula? So ionic name to formula, formula to name, if we were to do that, we would start with a formula, something maybe like Na2C2O4. Well, now I can follow the steps here. The metal, the hint is it keeps its name, so that would be sodium. The nonmetal will end in ide, or if it's a polyatomic ion, consult your memory. C2O4 is oxalate. Now I need to know and check something here at this point, because I may not be done. I need to look on the periodic table, check the metal on the periodic table, see if it has more than 1 charge. Well, I go to sodium. Sodium is in group 1. Group 1 is +1. If you're group 2, you're +2. If you're group 13, you're +3. But if you're one of those elements, like copper, cobalt, manganese, platinum, lead, silver, gold, well, not silver actually, gold, tin, and you have more than 1 charge, well then guess what? If you have more than 1 charge, you need to put in that Roman numeral when you write the name. So let me give you an example. Let's say I had something like this, Fe NO3 2. So now I look at this and I'm like, Fe, that's iron, and NO3, nitrate. Guess what? If you write this on the test, you're wrong, because you left out the Roman numeral. The iron over here, it has choices, and you need to know those and memorize those. Iron could be +2 or +3. Which one did I use? Well, a lot of you will say, well, there's a 2 down here, so it has to be +2. Well, most likely you're right, but you need to double check that. Nitrate's -1. So if nitrate's -1, the total for nitrate's -2, and for iron, the total would be +2. It would be iron 2 nitrate. Iron 3 nitrate wouldn't give us the right number, and you can check that. You can go through and check that, see if that will work or not. If +3 doesn't work, you know it's not +3. And I want you to be careful, because you could have something like this, SnS2. In fact, I want you to try this one. My hint to you is that there will be a Roman numeral. Let's see if you can figure out the correct Roman numeral to charge it to. All right, one more thing that I want to go over with you, and then we're going to practice this in class, really, and that is polyatomic ion manipulations. On the polyatomic ion table, I gave you all the 8 forms. But there are manipulations to this polyatomic ion chart. For example, let's take for example the ion ClO3-. Hopefully you said it to yourself just now that this is chlorate. It has 3 oxygens. If you look on the table that you're supposed to memorize, you'll see that different polyatomic ions have different number of oxygens. Chlorate has 3. Well, I could add an oxygen to this, and this will give me perchlorate. What I did was, 8 stays the same, but now there's a per. Adding an extra oxygen changes 8 to per8. Take away an oxygen, you'll have chlorite, ClO2-. So now we've gone from 8 to 8, 1 less oxygen. Take away another oxygen, hypochlorite, hypoite, ClO-. And these terms, they are rooted in Latin. Per means like permeate, persuasive, it means more. Hypo means less, hypothermia, hypodermic, they mean below or less. You need to memorize these manipulations. Now, one important thing is be careful, because there's an exception to this. One of them is manganate and permanganate. Notice this exception here, it doesn't follow the rule. But in general, if we start with 8, per8 is +1 oxygen. Ite is -1 oxygen. Hypoite is -2 oxygens. Generally, if you don't have any oxygens, then you're over here. You're with the ides. Be careful with the ides, and I'm going to finish with this. There are a few ides on the polyatomic ion table. Cyanide, that has more than 1 element, whereas all the other ides only have 1. Hydroxide, and lastly, peroxide. There's that per term again, meaning extra. Oxide, if you'll notice, is 1O, peroxide is 2. So this is your first naming video. There's only really going to be 2 or 3 of these, probably 2, but hopefully this will give you enough to get started practicing in class. Alright, thanks for watching. Have a great day.